Thank you. Thanks very much to Payman for inviting me to speak in this seminar. I'm very happy to be here. Like he said, my talk is going to be about some computer proofs for congruences for certain combinatorial sequences. And this is joint work with Jeffrey Shallett. So I'm going to describe a computational method to prove congruences for certain sequences that appear in combinatorics, such as the Catalan numbers, which count many things, but in particular, they count the number of strings of properly nested parentheses of length 2n, or they count the number of binary trees on n vertices, and a number of many other things. Another common set of numbers that occurs in combinatorics are the Motzkin numbers, which count, again, several different things, but for instance, they count the number of lattice paths from 0, 0 to n0, where you can move diagonally up one step, diagonally down one step, or one step to the right. And you are never allowed to drop below the x-axis. So these are a couple of commonly occurring sequences in combinatorics. And we're going to look at them modulo p for some primes p. And okay, the main thing that we are going to use here is Freshman's Dream modulo p. And we are also, most of our analysis is going to be based on the base p expansion of n. So I just want to write down here the notation I'm going to use to indicate the base p expansion of n is these round brackets sub p. And what's important here is that for this talk, all base p expansions are going to be written from least significant digit first. So from least significant to most significant digit. Now to start, let's start with the central binomial coefficients, 2n choose n. So the normal definition of the central binomial coefficient is that it's the coefficient of x to the n in the expansion of the binomial 1 plus x to the 2n. But for my purposes, I would rather this not be the coefficient of x to the n. I would rather it be the constant term in the expansion of some function. So okay, that's easy enough to accomplish. I divide my binomial by x to the n, and after some manipulation, I get this expression here. So 2n choose n is the constant term of this Laurent polynomial, right? Okay, so I can get a similar expression now for the Catalan numbers. All right, so the first line here is the usual definition of the Catalan numbers. It's more convenient for me to write them as a difference of binomial coefficients, because from my previous slide, I have an expression for 2n choose n as the constant term of this Laurent polynomial. And I can subtract a similar expression for the second binomial coefficient. I multiply by x here just to shift things a little bit, so I get n minus 1 here. And after simplification, I get another expression giving me the Catalan numbers as the constant term of some Laurent polynomial. And the other class of numbers that I'm going to study also has a similar expression as the constant term of some Laurent polynomial, and many combinatorial sequences that are defined as a sum of products of binomial coefficients have an expansion in this form, or they can be written as the constant term of some Laurent polynomial with integer coefficients of the form p to the n times some polynomial q. So this is the general type of expression that I can work with. So now I would like to look at the Catalan numbers modulo 2. So I start with my expression for Cn as the constant term of this expression here, and I reduce modulo 2. So of course, reducing modulo 2, I can throw away the 2, and I can change -1 to +1, and I get some function here that I'm going to call A1. So after reduction mod 2, I'm just going to give this expression a name and call it A1. Now I'm going to take A1 of n, the sequence A1 of n, and I'm going to evaluate it at the evens and the odds. So if I start evaluating at the evens, so I again reduce modulo 2. Here I apply the freshman's dream. When I multiply by 1 plus x, I can ignore the multiplication by x because that turns all the coefficients odd. And I'm interested in the constant term, right? So I don't care about any of the exponents with that are odd. So I can ignore the multiplication by x. I just multiply by the 1. And simplify, change a variable. I get a new function here, which I'm going to give a name again. I'm going to call that one A2. So this was A1 evaluated at the evens. Now, if I evaluate A1 at the odds by the same process, right, I factor out one term, I reduce modulo 2, I apply the freshman's dream, I simplify, change a variable, and now what I get is exactly A1 again, right? This guy down here, that was exactly my A1 that I started with. So I basically get a recurrence here. A1 at the odds, 2n plus 1, is the same as A1 of n. So I evaluated A1 at the odds and the evens, but I introduced a new function A2. So I'm going to do the same thing again and evaluate A2 at the odds and the evens, right? And after a similar process, I find that A2 of 2n gives me A2 of n again. So I get another recurrence. And A2 evaluated at the odds, again, if you look at this expression here, you'll notice that after I multiply the two terms here, all the exponents are odd. So there's no constant term, right? So the constant term is 0. So A2 evaluated at the odds just gives me 0. So this process terminates and gives me a list of recurrences. A1 of 2n is A2 of n. A1 at 2n plus 1 is A1 of n, etc. Right? So I have a set of recurrences describing now these two sequences, A1 and A2. And like I said, I would like to consider this in terms of the binary representation of n. I'm working mod 2, so I'm going to look at the binary representation of n. And so if W is the binary representation of n, written least significant digit to most significant digit, I can rewrite my recurrences like this. So of course, because it's least significant digit first, multiplying by 2 just means adding a 0 to the left. And so on, right? 2n plus 1 means adding a 1 to the left. And so I get the same set of recurrences, but just written in terms of the binary representation. And the point is, I can turn those set of recurrences, or I can describe the same set of recurrences graphically by this finite automaton. So the way this thing works is it's a machine with 3 states, one for A1, one for A2, and one for 0. And it's a machine that reads the binary representation of n, 1 digit at a time. And every time I read a digit, I follow the arc labeled by that digit through this machine, right? And if I terminate in one of these states labeled 1, I output 1, meaning that the Catalan number is odd, 1 mod 2. If I terminate in state 0, I output 0, meaning that the Catalan number is even, 0 mod 2, right? And so these arc labels come from my recurrences, right? So if I go back to my recurrence, this one says, if I'm in A1 and I read a 0, I go to A2, right? And you'll notice in the machine, if I'm in A1 and I read a 0, right, there's an arc labeled 0, I read a 0, I go to A2. And the second recurrence here says, if I'm in A1 and I read a 1, I stay in A1. So in the machine, if I'm in A1, I read a 1, I stay in A1, right? So there's a loop on A1. And the other arcs come from the other recurrences. If I'm in A2 and I read a 1, I go to 0. If I'm in A2, I read a 1, I go to 0. And once I reach 0, I never leave, right? So there's a machine for computing the Catalan numbers mod 2. I just feed n into this machine, and wherever it ends up, it'll either output 1 or a 0, meaning odd or even. And you'll notice that the only strings or the only sequence of digits that stay in the odd states look like a bunch of 1s followed by a bunch of 0s. That's it. Those are the only things that that reach the odd states. So this gives me a theorem, right? The Catalan numbers Cn are odd whenever n in binary looks like just a string of 1s. Okay, followed by a string of 0s, but those strings of 0, those 0s don't count, right? Remember, it's least significant digit first. So from the automaton, we can read off immediately that the nth Catalan number is odd exactly when n is 1 less than a power of 2, right? Just has binary representation 1, 1, 1, 1, 1. Right, and just so my notation here, 1 to the k means a string of k1s in the binary representation. 0 to the j means a string of j0s in the binary representation. Right, so from this we can deduce something that's, well, very well known about the Catalan numbers, right? The parity of the Catalan numbers. So this is something very well known. Okay, but that example basically describes the general method for computing congruences of this type. So we're given a sequence defined as the constant term of p to the n times q, where p and q are some Laurent polynomials. And if I do this calculations that I showed you before, modulo any prime power, I'll get, a set of recurrence relations. This process will eventually terminate. And I'll get a finite set of recurrence relations that I can then convert into a finite automaton, the way I showed you. So this is so Rowland and Zeilberger came up with this method for computing these automata for congruences for various combinatorial sequences. So they implemented it in Maple. If you go to Doron Zeilberger's website, you can find his paper, but also his Maple code and output for a bunch of different sequences, modulo a bunch of different prime powers. And similarly, Rowland and Yasawi also gave a different method for computing these finite automata as well. So we started with the Catalan numbers mod 2. So let's look at the Catalan numbers mod 3. Now, Alter and Kubota studied the Catalan numbers modulo primes P in general, and were able to get some very nice congruence results for the Catalan numbers mod any prime P. But let's stick with mod 3. So here's the first few terms of the Catalan numbers mod 3. And you'll notice that it has these long runs of zeros. All right, so these long stretches where the Catalan numbers are divisible by 3. And then sporadically, you'll see a 222, 111, or a 111, 222. And then again, long runs of zeros, and then sporadically 222, 111, 111, 222. So if we apply the same method that I just sketched for you, mod 3 rather than mod 2, I get the mod 3 automaton, the Catalan numbers mod 3. Can be computed by this automaton. All right, and then I see the labels of the states are the congruence classes. So this is a little more complicated than the mod 2 automaton. But we can derive results like the following. So Deutsch and Sagan wrote this paper in 2006, where, among other things, they characterized the places where the Catalan numbers were 0 mod 3, as well as the other residue classes, 1 and 2 mod 3. And they were able to completely describe this, not in the format that I've written here, but in a different but equivalent formulation. But for us, it's a bit more convenient to write it like this. So we can characterize exactly where these runs of zeros in the sequence of Catalan numbers mod 3 start. So they start in positions n, whose base 3 expansions look like one of these two forms listed here. Those are the starting positions. And then the lengths of the runs are 3 to the I plus 2 minus 3 over 2. Right, where I corresponds to this length of this run of ones here. Right, so we can completely describe where the zeros occur. We can also describe where this 111, 222 pattern or 222, 111 pattern occurs as well. We can describe all those positions. Again, in terms of the base 3 expansion of n. Right, so if n in base 3 looks like this, we'll see this 111, 222. So that completely describes the Catalan numbers mod 3. And the way we get this, so again, we have this automaton. It's not completely obvious how to read this information directly off the automaton, but we have another tool that will let us find or prove these things. So first, we have sort of the Rowland-Zeilberger algorithm to produce the automaton. Now we introduce another computer program called Walnut. This is developed by Jeffrey Shalit and, well, mainly by his student Hamoun Musabi, who implemented it. And this is a computer program that can answer questions about sequences that are computed by automata, like the ones I showed you. So the way this computer program Walnut works is You give it an automaton that computes the sequence. So it reads input n in base k and outputs the nth term of the sequence. So that's one input. And now you can ask it questions about the sequence. And how do you ask it questions? Well, the question is going to be a formula phi written in first order logic involving variables over n, constants, quantifiers, the usual logical operations, ordering, so less than, greater than, etc., addition and subtraction of natural numbers, and the variables are used to index into S, the sequence S, computed by the automaton. What we don't have is multiplication in this logic. So if you know something about logic, this is some kind of extension of the Pressburger arithmetic, where you have the arithmetic on the natural numbers with addition, but not multiplication. And what this computer program Walnut will do is it will take your formula phi. If it has no free variables, it will determine whether the formula is true or false, and it will tell you. If there are free variables, it will instead produce an automaton that accepts the base k representations of the values of the free variables that satisfy the formula. All right, so I won't explain how it does this, but here's an example, a very simple example of, here's a question that I could ask it, or a logical formula that I would like to evaluate as either true or false about the sequence C3 of the Catalan numbers mod 3. Right, so you'll see that this formula simply asserts that there exists some position I where there are 4 ones in a row in the sequence C3, right? So if I actually want to type this into the computer program Walnut, I've got to sort of translate this into its sort of language, but the translation's fairly obvious. Existential quantifier is represented by an E, universal by an A, the logical operations and is and, implies is implies, etc. All right, so it's pretty easy to translate the formula into the language of this program Walnut. There's this extra thing here, LSD3, which says that we are working in base 3, least significant digit first, as I said. So the point is, I can just simply type this command into the program. It's got the automaton for C3 as a file called cat3 in there, and it will calculate and it will evaluate the formula and say false. So there are no 4 ones in a row in this sequence of Catalan numbers mod 3, right? There are triple ones, but no 4 ones. So this program can answer these questions. Here's a more complicated one. So this command, again, is expressing a formula in first order logic, which captures the maximal runs of zeros. So if you look at this part of the command here, this simply asserts that at some position I, there's a run of n zeros in a row. And the part on the second line just checks that to the left of that run of zeros, there are no more zeros to the left, and to the right, there are no more zeros to the right, so that this is a maximal run of zeros. So this command expresses that there's a maximal run of zeros in C3, and it will produce this automaton. Now, this automaton is working with pairs of digits, because you see there are 2 free variables in this formula, right? There's an I and an N. I represents the starting position of the run, N represents the length of the run. And the way this automaton works now, it's going to read pairs of digits. And if you only look at the first component of each pair, that'll spell out the first variable I in binary. And if you read the second component of each pair, that spells out the binary representation of the second free variable n. And the double circled states are the accepting states. All right. And if I look at, so like I said, if I look at the strings accepted, and if I only look at the first components look like this. So these are the i's, starting positions of the runs. And the second components spell out this expansion in base 3. So these are the lengths of the runs. All right, so this is how I get this part of the theorem. All right, the program walnut gives me this this output, and that I can interpret as this result. Okay, so that was mod 3. All right, so mod 3, I can get this these results about when the Catalan numbers are divisible by 3, as well as characterize the other residue classes. So I can do the same thing now for mod 5. So if I compute the automaton using the same process for the Catalan numbers modulo 5, now I get something even more complicated than the mod 3 automaton. It's going to be very hard now to deduce anything just by inspection, but I can use the program walnut again to do the same thing. All right, to again tell me where the runs of zeros are in the sequence C5, the Catalan numbers mod 5. So I do that, and I again get this automaton here. The first component tells me the starting position of the run of zeros. The second component tells me the length of the run. And from that automaton, if I interpret the accepted strings, I can translate it into this result. All right, so the runs of zeros in the sequence C5 of Catalan numbers modulo 5 begin at positions n that have this base 5 expansion. All right, 3 followed by a bunch of 2s, or 3 followed by a bunch of 2s, and then something else. And the lengths of those runs are of this form, 5 to the I plus 2 minus 3 over 2. So again, we have these long these very long exponentially long runs of zeros where the Catalan numbers are divisible by 5. And then there's some sporadic non-zero residues scattered here and there, right? Which we can also characterize as well. Okay, so those were the Catalan numbers. Modulo, I guess we did the modulo 2, 3, and 5. So let's look at the sequence of Motzkin numbers. So like the Catalan numbers, we have an expression for the Motzkin numbers as the constant term of some Laurent polynomial. 1 plus 1 over x plus x to the n. Oh, sorry. This is before we get to the Motzkin numbers, we'll first get an expression for the central trinomial coefficients. So the central trinomial coefficients have this constant term expression. We can use that to get the constant term expression for the Motzkin numbers. So if I start with this as my definition of the Motzkin numbers, so they involve the Catalan numbers in the sum, replace CK with the difference of binomial coefficients. Then you'll see I get this central trinomial coefficient here on the left and something similar on the right as the second term. and I substitute my expression from the previous slide. After some simplification, I get the nth Motzkin number is the constant term of this Laurent polynomial. And so again, now once I have it as the constant term of some Laurent polynomial, I can again apply this algorithm of Roland and Zalberger to produce an automaton for the Motzkin numbers modulo P. So if we take P equals 3, so mod 3, I get an automaton for the Motzkin numbers modulo 3. Now, if I look at this automaton, one thing you can observe is that no matter where you are in the automaton, reading 0 followed by 2, so reading 0, 2 always takes you to the 0 state, no matter where you are. Okay, so this is an observation where no matter where you are, as soon as you read 0, 2, you go straight to the 0 state. So for any prefix W, I can read anything I want, any W, and then read 0, 2, and for sure I'm going to end up in the 0 state. So if I let W run through all ternary strings of any fixed length, remember these are ternary expansions, least significant digit first, I'll see that I get a run of consecutive positions that are all zeros. So again, I have these very long runs of zeros in the Motzkin numbers mod 3. Right, I can see that when if I look at some initial values, Motzkin numbers mod 3 have these very long runs of zeros and then sporadically some non-zero residues. Okay, now I calculate the Motzkin numbers mod 5. I get some very complicated automaton. Let's look at some initial values. Mod 5, I don't have these long runs of zeros anymore. So mod 3, remember, there are these long, exponentially long runs of zeros where the Motzkin numbers were divisible by 3. But mod 5, it doesn't happen. No long runs of zeros. Just an occasional 0 every once in a while, but mostly non-zero, not divisible by 5. So very different behavior. Mod 3 versus mod 5. Yeah, this is what I'm saying here, right? Unlike mod 3, the Motzkin numbers mod 5 does not contain these arbitrarily long runs of zeros. In fact, the only runs are these 111, 222, 333, 444. And those are the longest runs. So, okay, these two different primes, mod 3 and mod 5, the Motzkin numbers have these very different behaviors. And basically, if you look at other primes, depending on the prime, the Motzkin numbers mod P will either look like the M3, they'll either look like the mod 3 case, or they'll look like the mod 5 case. So this gentleman Burns, for example, did a lot of computations for primes up to 29 using these automata, and he kind of looked at which primes lead to which type of behavior. So some primes, the Motzkin numbers behave like mod 3. So P equals 7, 17, 19, for example. We get this mod 3 behavior where we have these long, long runs of zeros. And then some sporadic non-zero values. And for other primes, 11, 13, 23, 29, for example, we get a completely different behavior. We get the mod 5 behavior, where there are no long runs of zeros. So let's look at the mod 5 sequence a little bit more. So we can prove some stronger things about the mod 5 sequence than what I've shown you so far. So here's another nice property that the Motzkin numbers mod 5 have. So using walnut, I can prove that any length n pattern of residues that occurs is guaranteed to reappear within the next 200 n terms. Right, right, this is something in combinatorics on words that we call uniform recurrence. Right, so any length n pattern of residues that appears, I can guarantee its reoccurrence within a certain number of terms, in this case 200n. Notice that's not the case in M3 because of these long runs of zeros that prevent things from reoccurring, right? So I prove this using walnut, using two commands. So I have mot5 as the Motzkin numbers mod 5 automaton. The first command just asserts that the two patterns of length n at positions I and j are equal. That's all the first command says. And then the second one says that for every I, the length n pattern appearing at position I is guaranteed to reappear again at some position j, where j is at most 200 n positions later. Right, so I write that as a logical formula. I give it to the program Walnut, and Walnut will evaluate true. This is a true statement. So this is something I think that would not be so easy to show by sort of classical or sort of traditional means, right? This uniform recurrence property, right? I think you could probably work out, you know, some of the congruences, but something like this sort of recurrence property, to me seems like it would not be so easy to prove using sort of classical sort of number theoretic techniques. So for some primes, the Motzkin numbers mod p look like M5, where they have this nice sort of uniform recurrence property. But for other primes, they look like the mod 3 case, where there are these long runs of zeros. And so the obvious question is, you know, which primes fall into which category? It seems like the primes for which MP is uniformly recurrent are given by this sequence of primes, which is a sequence of primes that appears in the online encyclopedia. It's the set of primes that do not divide any central trinomial number. So remember, the central trinomial coefficients came up in the definition of the Motzkin numbers. And so there are certain primes that don't divide any of them. And those appear to be the primes where MP has this uniform recurrence property. Okay, so we can prove some sort of partial result in this direction. So Deutsch and Sagan, again, they looked at the Catalan numbers mod 3, they looked at the central trinomial coefficients mod 3, and they proved a result like this, right? They characterized exactly when the central trinomial coefficients are 0 or non-zero mod 3 in terms of the ternary expansion of n. And they proved this by an application of Lucas congruence for the binomial coefficients. We can get this also immediately from our automaton for the central trinomial coefficients. So the central trinomial coefficients also have this same sort of duality depending on the prime modulus. So for example, if we look at the sequence of central trinomial coefficients mod 5, we can compute the automaton, use Walnut then to answer all these questions or to prove all these properties. So we can show that, first of all, Tn is never divisible by 5. We can characterize the only residues that repeat 3 times in a row. or in general, the only patterns that ever repeat 3 times in a row. We can prove a similar uniform recurrence property. Again, if a length n pattern of residues occurs at some position I, it's guaranteed to reappear within the next 200 n terms. Property 4 is a first occurrence property, right? So I can bound when the first occurrence of a length n pattern of residues is, right? So if some length n pattern of residues occurs, it must occur within the initial 121 n terms. So again, I just simply write an expression describing this in walnut, and walnut will evaluate true. So let's look at the Deutsch and Sagan result for the central trinomial coefficients. They proved an analog of Lucas congruence for the central trinomial coefficients. All right, so they proved a result like this for Tn mod p in terms of the base p expansion. Okay, so what's immediate from this theorem is that Tn is divisible by p if and only if one of the Tn sub I is divisible by p, right? The Tn sub I come from the base p expansion. Right, so we can immediately test whether or not the central trinomial coefficients are ever divisible by some prime p. So we can, we can compute the primes that appear in this sequence, A113305 of the online encyclopedia. Right, this was the sequence that I showed you before of the primes that do not divide any central trinomial coefficient. They're the ones that we conjecture M sub p has the mod 5 behavior, the uniform recurrence behavior. So here's something we can prove using that Deutsch-Sagan congruence for the central trinomial coefficients. So we just compute the first p terms. Right, so if Tp is the sequence of central trinomial coefficients mod p, we compute the first p terms. If they do not contain 0 and do contain a primitive root mod p, then T sub p is uniformly recurrent. So this is something we can prove. Here's the mod 5 example. Right, so if I look at the first 5 central trinomial coefficients, reduce the mod 5, so 1, 1, 3, 2, 4. Okay, 0 is not there. I do have a primitive root mod 5. That's enough to guarantee that the entire sequence is uniformly recurrent. All right, so that's something I can prove, right? So I compute the first 5 terms. If I see a primitive root, then I know the sequence is uniformly recurrent. So we can do this for as many primes as we like that appear in this sequence, A113305, right? And every time the first p terms of Tp contains a primitive root mod p, so by our theorem, those TPs are uniformly recurrent. But I don't know how to prove that in general. So that's an open problem, right? Can you prove that for any prime p in this sequence, the first p terms of Tp always contains a primitive root? So this would also, so solving this would also imply a solution to my previous open problem of characterizing the primes for which the Motzkin numbers, mod p, are uniformly recurrent or not. And that's actually, that's about it. So I'll just end with some references. So you can find the program Walnut that I've been using for all of this on Jeffrey Shalet's website. You can find Roland and Zalberger's paper on Doron Zalberger's website, along with their Maple code and some output. You can also find Deutsch and Sagan's paper. So most of this is sort of inspired by Deutsch and Sagan's results. And that's it. Thank you very much.